Hello students, this is the lab I've been warning you about all semester. It's the buffer lab, and we are going to be dealing with buffers. So this is not actually that hard of a lab to do in the lab. It is hard to do the analysis because weak acids are kind of tricky and complex, and we really need to be considering in each case, are we in an equilibrium situation? Do I have a buffer? Do I not have a buffer? How do I go about calculating what are the active species in the beaker and what is the pH? Okay, so what we're going to get out of this lab, hopefully, and there's an awful lot of, we're trying to work with what you're doing in lecture. Writing a dissociation equation for either an acid or a conjugate base and its equilibrium constant expression. And so mostly we're going to start with a weak acid, but in one case we're going to switch it for the conjugate base. So can you write the equation for the dissociation of an acid and its Ka expression? Then do you understand why a buffer results in a smaller change of pH? We're not going to calculate the volumes of weak acid, so skip that one. Sorry, I didn't take it off. Predict the pH of a buffer mixture. A plain weak acid, a weak acid with an added strong acid, a weak acid with a buffer with an added strong base. So we're going to do a variety of different pHs. What happens when you do this? And be able to use a pH meter. Okay, so reminding you that a weak acid is something that dissociates incompletely. Now that you've had equilibrium and you've discussed that and you've talked a little bit about acids, we can go back and sort of remind ourselves that they produce protons, but because it only dissociates incompletely, I can't judge how many protons are going to be made by how much acid I start with, unless I know that equilibrium constant, the dissociation constant. So as with any reversible reaction, I can write an equilibrium expression and come up with a K value for it. In this case, excuse me. So in this case, we have an acid making two products, H plus plus A minus. Yeah, in reality, it really is reacting with water, and that extra water actually sticks to the H plus and really makes hydronium ions, and I'm sure, but this is a little bit clearer to write it as H plus rather than hydronium ion. So we would have a Ka would be concentration of my products raised to their coefficient divided by the concentration of the reactants raised to their coefficient. So I have H plus times A minus divided by the concentration of HA. This is going to be true for all acids. And in a case of, well, we only care about it in an equilibrium condition when it's not a strong acid, when it's a weak acid. And we can then experimentally determine Kas, or we can experimentally, in our case, we're going to use Kas that have been already derived from a table and use them to make some predictions. So again, don't forget, water itself is a weak acid. So we have our dissociation of water constant Kw. Water can split, two waters can split up into hydronium ion and hydroxide ion. And if we measure that, that's 1 times 10 to the negative 14. So from that we know if I have a mixture of water, it's going to be, I'll have equal concentrations of H plus and OH minus. So pH is going to be 7, when I take the negative log of this. How do I need to rearrange acid-base equilibria sometimes and how it affects K? So a lot of times when we switch and we talk about conjugate bases, we're going to have to do some switching around. So I just kind of wanted to get ahead of the game and sort of put this out there. So again, this is our basic acid reaction. HA makes H plus plus A minus. I could add the reverse reaction of the dissociation of water to it. And if I do that, notice I end up with the conjugate base reaction. So now, instead of HA reacting with water, I have the conjugate base reacting with water. And if I do all this, remember, if this is 1 over Kw because it's the reverse reaction, and I follow through, my K is going to be Kw over Ka. So sometimes I need the Kb of the conjugate base of a weak acid. I can find that by taking 1 times 10 to the negative 14 and dividing it by the Ka value for that weak acid. So this is often useful when I'm dealing with conjugate base system, is I want to rewrite the equation in terms of how the conjugate base is reacting with water rather than the acid reacting with water. And then I could also find its associated K in that related way. That becomes very helpful, especially for the last one we're going to do. The pH, of course, is equal to the negative log of the H plus concentration. To be fair, it's really the negative log of the hydronium ion concentration. And it just helps us get these concentrations from very big and very small numbers down to reasonable numbers. So instead of, because normally we range from 10 to the 0 to 10 to the negative 14, that's a huge range of numbers and a lot of scientific notation. Basically, remember, a log is the exponent, so we're just saying, I just want to care about the size of the number. I'm not too worried about the initial number in front. If I need to calculate the hydronium ion concentration from a pH, I'll take 10 and raise it to the negative pH power, and that will get me the hydronium ion concentration. Okay, so finally we can say something about a buffer. What is a buffer? Buffers are designed to their mixture of a weak acid with its conjugate base in approximately equal amounts. And they're designed to be able to adjust to the addition of strong acids and strong bases so that that concentration of protons doesn't fluctuate wildly. So buffers are designed to resist pH change. And it's also this mixture of a weak acid and its conjugate base. So how does that affect how it adjusts to pH? So if a strong acid is added, it can react with the conjugate base that's already present in there. And so rather than, a strong acid, all of a sudden the H plus concentration shoots up, it doesn't, because that H plus reacts with the conjugate base, which sort of absorbs it. Then I just have a little bit of change. It will get more acidic, but just by a little bit. If I instead added a strong base to a buffer, it can react with the weak acid that's in the buffer. But again, that sort of like eats it up so that it doesn't swing into a very basic solution. It still will get more basic. The pH will raise up a little bit, but not nearly as much as if I didn't have a buffer system in. We're going to talk about how you predict the pH of a buffer. So I could go all the way ice table, and I'm going to show you a shortcut, but I just understanding where it's coming from. I have my weak acid making its conjugate base. So note that in my ice table, I assume like I've mixed these, but there has been no dissociation taking place. So the H plus would be 0, but I do have some initial concentration of that conjugate base. So I could calculate the change, and then I could put it into my Ka formula. I get an ugly quadratic. I could solve the quadratic, and I could come up with what the pH is. 2.32 would be, and this was using, I don't know if this is using the weak acid approximation or not. I think I did actually. Okay, here's the solution to the quadratic, 2.35. If I say x is small enough that I'm going to ignore this x here and this x here and just say it's 0.24x over 0.16, and I solve for that, I get 2.32. Notice 2.35, 2.32, they're pretty close. But a much simpler equation is to say, let me take logs of everything. The pH is equal to the pKa plus the log of the conjugate base concentration at equilibrium divided by the acid concentration at equilibrium. So this is always true. Henderson-Hasselbalch said, let me actually go a little bit further. Instead of using the equilibrium, if it's a weak acid, the equilibrium concentration is not all that far off. Can't we just use the initial concentration? And it turns out, under a lot of condition, it gets you a pretty good approximation. So again, on the left-hand side, we took the Ka expression, we took logs of both sides, we did some fancy math, we rearranged it, and found what is pH as a function of all the equilibrium concentrations. But this Henderson-Hasselbalch noticed that these equilibrium concentrations are now the initial conditions. So as long as I know what the initial conditions of what I mix, I can use this to predict pH. This is heavily used in biology, and it works very good under a lot of conditions. It has its limits, and you need to know what the limits of being able to use this easy equation. One is it has to be a weak acid system. This doesn't work for strong acids. Two, and that means pKa between 4 and 10. Remember, pKa, P means negative log of. So that's the negative log of the Ka value that you would look up on a table. You have to have intermediate concentrations. If it's very strong or very dilute concentrations of those weak acids in the conjugate base, it doesn't work. And the ratio of the conjugate base to the weak acid have to be, near 1. So somewhere between 1/2 and 3, like they're not exactly 1. But if you have 10 times more weak acid than you do of the conjugate base, it's probably going to stop working pretty well. Also, remember, if I wanted to get equilibrium concentrations, I'm going to use an ice table. Be careful, though. When I mix two things together, if I just have one thing, I know my initials. It's just whatever the one thing I start with. But if I have two things together, when I mix them, I actually dilute them in that initial mixing stage. So we contemplate that we mix them, kind of like we were doing with the equilibrium lab, that when you mix them together, you change and dilute them, and then they would do whatever equilibrium reaction they're going to do. So when you do your initials, make sure that you're using the diluted concentrations, meaning that dilution by mixing. You're going to, negative X. So this would be, if we're going to do this the long step. And in some cases, you have to use an ice table. In other cases, we can use that Henderson-Hasselbalch. So this is the steps that we're going to go through. We'll spend more time on that in the second week when we're doing the analysis. But we have some examples here, so I'm not going to go through all these examples. The conclusion, hopefully, is that when we go through all this, we're going to see that when you add strong acid, you make a pH change that is going to be slightly more acidic, lower in pH, but not drastically more acidic. And if you add a strong base, it's going to get slightly more basic, higher pH, but not by very much. And if we were to do this with something else like water, which we will do in lab, we should see drastic changes. It's not a buffered system. Okay, so what you're going to do this week, you're going to be making a buffer solution. I'm going to assign you a set of volumes, a volume of 0.3 molar acetic acid and a volume of sodium acetate. They're different concentrations, but and you're going to measure it out, the volumes with a graduated cylinder, mix them in a beaker, in a flask, stir them well, and then you're going to portion out 20 milliliter aliquots of it into 4 different beakers. One we're going to just use plain buffer. The second one we're going to add 1 milliliter of HCl to. The other one we're going to add 1 milliliter NaOH to. And one we're going to add 1 milliliter of water. Then we're going to measure those pHs. We're going to have to calibrate the pH meter. This is a set of instructions. And then after we've calibrated with buffer 7, buffer 4, and make sure the pH meter is reading well, then we can start measuring our solutions. So we'll measure those 4 solutions we just made. When I'm done measuring the first 4 solutions, once I'm checked that everything's good, I can get rid of those, clean the beakers well, and then start with water. I'm going to get water in 3 different beakers. In one beaker, I'll leave it just water. One beaker I'm going to add a milliliter of HCl. Another beaker I'm going to add a milliliter of NaOH. So I can compare how did the buffer respond to how did it happen when I was just adding it to water. And then you're going to do just pure acetic acid, the 0.3 molar acetic acid, and pure 0.2 molar sodium acetate, the ingredients that are in the buffer but not mixed together. And you're going to measure those pHs. And that's what we do this week.